Hello and welcome to Bloom and Brew at WHSK. This is Giselle at Commonwealth University, Bloomsburg campus. You ever wonder what makes the moon, or what it's even made out of? Thanks to researchers at Tokyo Metropolitan University, they've cracked the code. Tiny X-ray telescope. Now, we all know what an X-ray and telescope is, but what can they do combined? I don't know. But researchers know the answer, though. Newly developed an X ray telescope will allow us to have a geochemical map of the entire lunar surface. But wait, I thought we had one of those, right? No. According to ScienceDaily.com, the moon's geological history is not fully understood. This is because scientists don't have a complete geochemical map of the lunar surface. Researchers can't collect samples from every part of the moon, so they have to rely on remote sensing methods, X ray fluorescence imaging. X ray fluorescence imaging is the process of detectors are pointed at the moon to capture X rays emitted by specific elements after they are struck by solar radiation. Those signals can help reveal which elements are present across different regions of the surface. Missions like the well-known Apollo produce useful partial maps, but a full global map is still missing. Creating one is technically difficult for several reasons. Missions have limited time to gather enough sunlight-driven X-ray signals, and detectors can degrade during long periods in space. The problem is especially difficult near the moon's poles, north and south. In these regions, solar X rays are weaker, which makes it harder to collect the signals needed to identify surface elements. Scientists are able to address these obstacles using the X ray telescope on a satellite orbiting the moon. Traditional X ray telescopes are too heavy and large for this type of mission, and initially, the team's compact telescope was designed to study Earth's magnetosphere, but its small size makes it practical for long term lunar satellite observation and would allow wide area observations of the lunar surface during strong solar flares when the sun provides more intense X ray illumination. They've done a wide range of tests testing in radiation conditions far harsher than those expected in lunar orbit. So, the durability could support robust wide areas and give us high resolution imaging over an extended mission. Resolving these obstacles could help researchers find answers in the moon's lunar geology. NASA says understanding the moon's lunar geology gives scientists a window into formation of the early solar system. It helps calibrate historical space timelines and maps out crucial resources like water, ice, and metals needed to sustain long-term space exploration. Just like there's fossils on Earth, there's a chance fossils are also on the moon. And the nice thing about fossils is they give us a time map of everything. Unfortunately, because the Earth's active plate tectonics, they've erased some of our ancient history, but the moon acts as a pristine fossilized record. How cool is that? The fossils here on Earth are pretty gnarly, but imagine the fossils on the moon. This isn't specifically for us, but for scientists. With new innovative technology, we should proceed cautiously. Like all missions, there's a chance of failure or a chance of success. All come with risk. I'm definitely hoping for success. And I'm rooting for the team at Tokyo Metropolitan University. I don't know about you, but I'm excited to embrace what we discover and all the more there is to know about our beautiful Luna.